Welcome students to this short video about Layout Editor. This short video is intended to make you aware of some common tools used during the layout. Having a knowledge about these tools would certainly boost the speed of your layout design and improves your skill in better designing the layout without much DRC errors. So first, let us try to look into those tools. As shown in this layout editor, you could be able to see that there are two white lines that are intersecting at a particular point, and we call this particular intersection point as the origin. Also, you could be able to note that there are dots, which are few dots are bigger and few dots are smaller. So these bigger dots are basically spaced by major spacing spec, and the smaller dots are basically spaced by minor spacing specifications. So we can make use of these dots to our advantage in constructing the layout. So let me try to explain how these options would affect the placement of any layer with a metal 1 layer as a demonstration. Now before that, we'll try to adjust these dots by clicking on this options display. So you can also use the shortcut key E to invoke this particular display menu. Now clearly we are going to work under this grid control, and whatever the numbers that are being displayed here is in terms of micrometer. The units of these numbers are basically in terms of micrometer, and we just want to modify to suit our requirement. So in general, you can modify this minor spacing to 0.1 micrometer, and the major spacing we can make it to 0.6, which is nothing but our chosen pitch size. And you can also change this X snapping spacing and Y snapping spacing to 0.01 and 0.01. So once this is done, do not change any other settings. You can directly go and click OK here. So now let us try to create a metal 1 layer carrying a VSS signal, and we know that VSS should be wide enough to carry this particular signal. And how much wide it is? It's supposed to be 1.2 micrometer. Now we have done this options menu and we have clicked OK, but we couldn't be able to see any change in this particular screen with respect to the dots. So in order to make this effective, you just scroll your mouse button back and forth, and you could be able to see suddenly these dots has got changed, which means that we have increased the dot intensities. And when you zoom in, you could be able to see within the major dots, you could be able to see that there are 6 small dots, right? So this is what I was showing through this option display. So now let us use this for our advantage in constructing this metal 1 VSS layer. Now towards the left, you could be able to see that there is a layer panel, and you could be able to see that there are many layers that are being listed here. Now since we want to route this VSS with a metal 1, make sure that you select this metal 1 layer. Also note, when you scroll down, you will find there is one more layer which is named as metal 1, the same as before. But certainly there is a difference between this metal 1 and this metal 1. It's nothing but the purpose. Here, the purpose of this particular metal is for draw, and the purpose of the second metal that is being displayed here is for pen. So please make sure that you select the first option, which is meant for the draw. And once you select this option, just click on Create, Shape and Rectangle, or you can even use the shortcut key R to do this. So now let us try to create a width of 1.2. So what we can do is, you can just zoom in, make sure that you selected the particular dot, and then when you try to drag this particular mouse, you can end up reaching to the third major button, which is 1.2 micrometer away from the first dot. So now that we have reached to this third dot, and we know that this particular height of this wire would be 1.2, but I want to stretch this, or I want to extend this wire all the way to a width of say 6 micrometer. So now that we are in trouble, so what we can do, we have to extend this wiring all the way by counting these major dots, so this would be like 1.2 2.4 and 3.6, and all the way we have to reach to 6. Okay, but there is one more tool that we can use to our advantage, which is nothing but the ruler tool. Now, so what I do is I'll just simply discard this shape by pressing escape, and let us try to use the ruler tool to make sure that we draw the width of the wire to 6 micrometer. In order to invoke this tool, use the shortcut key K, and that brings the ruler to your mouse pointer. Now I'm just going to select from here this particular major dot, and then I'm just going to move all the way towards the right, and once I reach this 6, you can just click again the left mouse button, and that completes the ruler. So now, with the help of this ruler as a guide, we can create a wire whose height would be 1.2 and the width would be 6. So how to do that is make sure that you still have selected the metal one draw, and click on this create shape rectangle, or you can even use the shortcut key R. So I'm just going to use that shortcut key R, and I zoom in so that I select the appropriate major dot and press R, and then drag it all the way down to create first of all the height to be around 1.2, and then move towards the right till you reach this 0.6. So if you couldn't able to move further towards the right, you can use the keyboard arrows to adjust your screen. So I'm just using the right arrow to adjust the screen, and once I reach this spot, I zoom in and make sure that it is exactly pointed at 6, and I just use my left mouse button to end this shaping part. You can also use the shortcut key F to fit the shape that you have drawn. So once you click on F, you get able to see that the shape has come to the middle screen. So once you complete this action, it's always better to remember that you always press escape. So I pressed escape, and now the next tool that I want to discuss is about the stretch tool. Say for example, now that you want to adjust this width of this wire from 6 to 5 micrometer, for which you need to delete this shape and then redraw it, but we have a tool named as stretch which you can find at the top of this menu. So before you select this particular stretch tool, make sure that you are not selecting any layers that are available here. Say for example, if the layer is selected, you will find that the selected layer is exposed with pink color boundary. So what you can do is you can select somewhere in the empty space, and then make sure that you deselect any layers that if it is selected before you do the stretching. Okay, so I selected the stretch, and then when you move this particular mouse over a particular edge of the shape, you could be able to see only that particular edge is selected. Now since we wanted to reduce the width rather than the height, I'll just move the mouse and hover it on the right edge of the rectangle. So once I move to this edge, I left click and then move all the way to 5. So once you reach to the number 5, you can just click it again to end this stretching. And now you have to press escape to come out of this stretch tool option, which is being attached right now to your mouse pointer. So once you press escape, you could be able to see that the mouse pointer is relieved from this stretch tool. Now the last tool that I want to really emphasize is about DRD edit. So this is particularly important when you try to route two different signals using the same metal layers or using the same type of layers. So let me demonstrate that. So what you can do is click on this options, and there is an option known as DRD edit. Okay, so select this and make sure that you select this notify option and click OK. And I just want to draw one more layer by making use of the same metal one. So I have selected already, and click on this shape, and then rather than going for a rectangle, I'm just going to select the path tool. This path tool ensures that the width of the wire is stick to 0.3, which is the minimum width of your metal one layer. So I select this, and then I just want to make a routing from somewhere at the top all the way to the bottom. Now I just select a random position. You could be able to see the moment I try to move down, it shows whenever the width becomes smaller than 0.3, it just notifies that the width of the wire is not meeting the minimum width specification. So what I can do is I can stretch it again, and when I try to move all the way down and try to reach the metal that I have drawn earlier, it again shows when the spacing is not more than 0.3 micrometer. So what we can do is we can stop it well before this. So this is how we can make use of this DRD option to draw any layers without any DRC errors. So with the knowledge that is gained in this video, let us try to build our inverter layout in the next video. In this video, we will try to build inverter layout based on the knowledge gained from the preliminary introduction videos. Hope that you are familiar with routing grid and its offset of half pitch size with respect to cell origin, and also the PR boundary and its extension outside, and its spacing of MOS transistors from inside the boundary. So now let us look back to our previous slide, that is the summary of rules, showing all the rules being summarized here. Just make a note of these rules by pausing the video for a while. Coming back to Virtuoso, make sure that you have opened the design schematic of your inverter. So what I really mean is, it's not the test bin schematic, but you have opened the inverter design schematic. So now from here we need to create a layout for this particular schematic. So click on launch and select Layout Excel. Now with this default settings, just click OK, and this window says that you are going to create a cell which is the same cell name that we had for the schematic, but the view that we are going to create is supposed to be a layout view. Okay, so no need to change anything. So just click OK here, and that's open up two windows. One is your schematic window, the other one is your layer editor. So now expand this, and as I said before, we also have to do some settings before we actually start laying out the inverter layout. So the very first thing is to get into options, display, and make sure that this corresponding settings is created under the grid control. So just click OK once you have this particular setting over the grid control part. The next thing is we have to make sure that our DRD edit is selected with notify option as stated in the previous video. So once these two things are done, the next important thing is to generate the layout from the schematic. So for which you can just click on connectivity, generate all from source. You could be able to see the same similar symbol towards the left bottom corner. Okay, so you can either click on this or click on this particular option. So I'll just go with the first option. So in this, you go to the IO pin tab and then make sure that the V in and V out pins are marked to metal 2 pin. So we are going to select as a pin here rather than a draw configuration. So just select this option and then click on update. So our input pin VI has got updated from metal 1 drawing to metal 2 pin. So similarly, do it for V out as well and click on update, and that's done. Note that the pins of VDD and ground were also being mapped to metal 1 drawing layers. So we can retain the same under this pin label option and then click on these options and make sure that the height is set to 0.5. So this will ensure that all the input pins and output pins and even the VDD and ground will have a text over those pins, which will ease us to identify the pin names. So that's the reason why it has to be done over here. So just click OK and click OK here, and this in turn creates few things. One is our PMOS the second is our NMOS, and there is also one more layer which we were talking about in the introductory video. It's nothing but the PR boundary, and along with it you can also zoom in and see that we have this input pin and output pin along with ground and VDD as metal layers, right? Now one thing that you have to note here is both this PMOS and NMOS seems to have a kind of rectangular box without any internal details showing the source, gate and drain terminals. Now to expose these you need to use the shortcut key Shift F. So that will expose the internal structure of this boxes that we had before. So now that we have all the things, and so now I'm just going to show the steps that we are going to follow during this inverter layout design process. Now I'm going to show the steps that are going to be followed in this particular slide. Follow these steps to do your layout effectively. So first thing is we need to extend the PR boundary vertically to a height of 15 micrometer. So that we will do it. So coming back here, this is our PR boundary. We need this PR boundary to have a height of 15 micrometer, and we know that each of these major dots represents 0.6 micrometer distance between the two consecutive dots, right? So we can use our ruler, for which we can press K. So now the next thing is we need to extend this particular PR boundary all the way from this height to a height of 15 micrometer. So for which what we can do is we can select the stretch tool, and so make sure that when you hover your mouse pointer onto this PR boundary, it has to show a yellow dotted line. If it doesn't show that, then some other layer is selected before this, right? So you could able to see that my VDD is selected, and that's the reason why when you hover your mouse on this particular line, it doesn't show that yellow dotted line. So what you can do is press escape to come out of this stretch tool and click somewhere so that you deselect any of the layer that you have selected before. So now switching back to our stretch tool, now if you hover your mouse on the top edge of your PR boundary, you could able to see that yellow dotted line being highlighted. So just left mouse click and then move or stretch it all the way to 15 micrometer. You can just zoom in and make sure that it exactly hits to 15 micrometer. So once you stretch to the desired height, you just click again to end the stretching. Now press escape to come out of this. So we have done the step number 1, and now we will look back to step number 2. The step number 2 tells us to place the M1 P-sub wire and M1 to N-well wire at the left side of our PR boundary, one at the bottom, the other one at the top respectively. Go to create and click on this wire, and now we need to select appropriate wires from this drop down menu. So the first wire that we are going to place is M1 to P-sub. Now you might wonder where exactly the P-sub is. So as I said before, this entire space which has been marked with black color is all assumed to be a P substrate, and we just need to place this wire exactly at the origin. So you can zoom in, make sure that you are fixing it at the center. So press escape to come out of this wire, and then now again click on this create wire and select M1 to N-well wire. So now that I have got this wire, so now just move your pointer all the way to the top left corner and try to fix it at this left PR boundary corner. Press escape to come out of this wire, and we'll look back to the step number 3. The step number 3 is to draw VDD and ground power lines of 1.2 micrometer width using metal 1 layer. And it also been mentioned that we have to extend this VDD and ground horizontally for about 0.6 towards the left, and also vertically for about 0.6 on both the top and bottom of our PR boundary. So press F and then make sure that select your metal 1 draw layer, and then click on this create shape and then rectangle, or you can use the shortcut key R. And now what we have to do is to extend towards the left horizontally by 0.6, and we know that these major dots are spaced 0.6 away. I will use this particular dot as my first starting point, and this has to have a height of about 1.2, for which I need to cross two major dots. You can just zoom in, and once you get down, you can start all the way, move towards your right, and you can just create some distance, and we will later adjust this particular width based on our placement of PMOS and NMOS. So just make sure that you have placed this metal, which is of having a height of 1.2, just by looking across the dots. Yeah, so we have done with it. And now, in order to create a metal for VDD, what we can do is we can just simply copy this particular metal and move all the way up to the top PR boundary structure. So to copy it, you select the layer, right click, and click on copy. Or you can also use the shortcut key C. Left click on this layer and then move your mouse pointer till you reach to the top PR boundary, and make sure that you are placing exactly on the major dots. So we have done with it, and now we'll switch back to our slide to look for step number 4. The step number 4 is to place the NMOS close to the ground power line, which is about 0.9 micrometer away from the edge of metal 1 of ground to metal 1 of source and drain. Note that this spacing between the ground metal and source drain metal would help us to route poly and metal 1 intersignals while building a complex layout. So we will perform the same by following the step number 4. So before we place this NMOS transistor, we will try to use our ruler to create a spacing of 0.9 from this VSS metal layer, for which you can use the shortcut key K, and then make sure it runs from the top of this metal and goes all the way to 0.9. Once you reach to the distance, left click to end this ruler, and now you can zoom out and then try to collect your NMOS transistor and drag it all the way, and make sure that the metal of our source terminal is exactly spaced 0.9 away from this metal. So still we have certain distance. So what you can do is you can just further pull down this, and you can even adjust your ruler such that you can fix the transistor. So now that we have reached to this 0.9, and we'll just move on to step number 5. The next thing is we need to adjust the NMOS transistor horizontally such that the N implant layer is spaced 0.2 micrometer away from the PR boundary from its left. And we know that this spacing ensures that any NMOS transistors from its neighbor cell on its left is placed away by 0.4 micrometer. So we'll perform this step number 5. Now, as before, first let us use our ruler right from the edge of this PR boundary to create a ruler distance of 0.2 micrometer. So press K, zoom in, and once you reach to 0.2, just click it again, and that would ensure this 0.2 spacing. In the case of our NMOS, the yellow color represents our N implant. Okay, so what we have to do is to make sure that this N implant is spaced exactly 0.2 micrometer from the edge of our PR boundary. So you can zoom in, make sure that it's been exactly placed 0.2 from the left of our PR boundary. So now we'll switch back to our slide. The step 6 is really not a step that needs to be implemented, but to get understood. The requirement of transistor from its neighbor cell should be spaced by 0.4 micrometer imposes that the NMOS N implant is also to be placed 0.2 micrometer from the PR boundary to its right side. We have to stretch the PR boundary width about 2.4 micrometer because of the following requirements. The first requirement is nothing but the PR boundary needs to have a width that is always a multiple of pitch size. And the second one is the requirement from step number 6. that is towards the right of our NMOS N implant, we need to have a minimum spacing of at least 0.2. So with these two requirements, we will try to define the width of our PR boundary. So by making use of the stretch tool, one can select the right side of the PR boundary and make sure that you place it exactly at a multiple of your pitch size. Placing the PR boundary of the right side at this ensures that the PR boundary is always a multiple of pitch size, and also the spacing between the N implant and this right side of the PR boundary is greater than 0.2, which has satisfied our requirement from step number 6. The next thing is to repeat the same for our PMOS transistor. So what we can do is press escape to come out of the stretch tool and select your PMOS transistor. And in the case of PMOS transistor, you could able to see that there is an orange box outside this P implant, which is in reddish color. So the reddish box represents our P implant, and this orange thick box represents our N well. So while placing this PMOS transistor, we have to ensure that this P implant is 0.2 micrometer away from our PR boundary on the left side. So before we move this PMOS transistor, we also have to ensure that the metal of the PMOS source drain terminal has to have a spacing of 0.9 micrometer away from the VDD metal. So first we will use the ruler to create the guideline to place our PMOS transistor. So from the bottom of this VDD metal, drag this ruler all the way till it reaches 0.9. And similarly, we also have to create a guideline for placing the P implant from the left of our PR boundary by about 0.2 micrometer. So once these two rulers are created, then now you can move your PMOS transistor. You can select the PMOS transistor and use this move tool to move the PMOS transistor vertically up, and then later you can adjust the placement based on the ruler that we have, exactly spaced by 0.9, and then you can again move towards the left such that you are spacing your P implant by about 0.2 from the PR boundary. So we have done both these requirements, and now that we have completely placed both the PMOS and NMOS into the structure. So the step number 5 is to draw an N well such that its width starts from the left covering the M1 N well to the right covering the PR boundary by a spacing of about 0.6 micrometer. And also the height supposed to match to our rule that it has to be about 2/3 of our cell height, and we have already seen that this 2/3 of our cell height would lead to 10 micrometer. So in order to create 10 micrometer height right from the top of our N well, we can use the M1 N well via as our starting point. So we can use the ruler by using the shortcut key K and start dragging all the way till you reach 10 micrometer. Once you reach to 10 micrometer, click it again and press escape to come out of this tool. And now from the layer panel, select the N well drawing layer and use the rectangle tool to draw an N well whose height is about 10 micrometer. So selecting the 0.6 away from the PR boundary on the right is pretty easy. Just by using the major dot, we can place our structure exactly 0.6 away from the right of our PR boundary. So just click to end this particular part and press escape. And now the next task is to place the IO pins and the VDD and ground pins. So placing the VDD and ground is pretty easy. Just drag it and place it on the metal layer. But the placement of this VI and VO pins has to follow the routing grid pattern. So I will again show back the slide and we'll talk about the routing grid pattern, which is offsetted by half the pitch size. We have already seen that the major dots right now will be exactly at these intersect points. But as I said before, usually the power tool will follow this kind of pattern for routing grid. To get these positions, we have to look for our minor dots that are being offsetted from our major dots by half the pitch size. So now what I really mean here is, like when we try to overlap this structure onto this structure, these intersect points would be exactly at the mid places. So with that as our rule, what we have to do is we have to place our IO pins exactly at the center of this squares, where we will have 4 major dots on each corner of our square, right? So we'll do that. Now switching back here, to get down to the center of this 4 major squares, we have to ensure that the minor spacing is adjusted in such a way that we can get a reference point exactly at the mid position of our 4 major dots around this particular square. So we can use the display option menu and change the minor spacing from 0.1 to half the pitch size, which is 0.3, and then zoom in and zoom out. You could able to see at the center of the 4 major dots, you could able to find one minor dot that is placed exactly at the center. Now with this as our reference, we can place our V in and V out pins. Now select the V in pin and make sure that you are placing exactly at the center. So I'm just dragging it and I'm trying to fix this at the center of this 4 major dots. You can randomly choose any 4 major dots within this PR boundary. Similarly, select your output pin and try to fix somewhere in the next row midpoint. So the last task is to route the internal wires for the input output as well as the source of PMOS and NMOS. So select the appropriate layers for routing the source of NMOS and PMOS to the respective supply wires. Select metal 1 and use the path tool by pressing P and click somewhere from the mid and move the mouse. Once you reach to this top metal of your ground, just click on enter key to end the wiring, and by similarity we can do it even to short the source terminal to the VDD metal. So once you reach, it can even overlap, doesn't matter, but make sure that it touches onto the VDD metal. Okay, and now we can also short the drains of both PMOS and NMOS by using the same metal 1 path tool. Once it reaches the drain of NMOS, click enter to end the wiring. So now that we have done almost everything except for the input, which is to be run through poly. Now select the poly and again make sure that you select the path tool to route between the gates of PMOS and NMOS. So select the mid place and then drag it all the way till it reaches the gate of our PMOS. So now that we have done everything except for certain things. As I stated before, the VIN and VO pins are basically made out of metal 2, but what is running at the bottom is metal 1 for the output pin and a poly which is running under the metal 2. Now how do we make a contact between the 2 different layers? It is through wire. Now let us first try to create a wire for this VI input pin, which is made out of metal 2. Before we do that, we can use a rectangle tool to create a box such that it covers or it touches the poly that we have drawn before. And now click on this create wire, and when you look into the option of wire from poly, there is no option for us to connect directly to metal 2. So we have to use first poly to metal 1. So this is done. The next thing is to pull out one more wire between metal 1 and metal 2 and try to fix it onto this. And we also have to put a wire for the output pin as well, just because the bottom layer that we have is a metal 1. So now it's time for us to readjust this ground and the VDD pin, which has been stretched more than the specification. So make use of this stretch tool and bring it all the way closer to PR boundary, but still spaced by 0.6. Yeah. So press F and we have fit almost all the things inside this particular structure. So once you have done with it, save it. And now there are two verifications that we have to do before we actually work on this layout again. So one of the verification is nothing but DRC, or design rule check. In general, the DRC will check for the violation of any minimum spacing and any violation across the minimum width of the layer that we have used. So in order to do this process, click on Asura and select Run DRC. Make sure that you provide some run name. Here I have given ABC as the run name, and also ensure that the technology option is selected and it's pointing to GPDK 180. Now with these two options being reflected on your Asura run option menu, click OK. So now we have run this DRC successfully, and click S and see if there is any DRC error. So we have got a message stating that there is no DRC error. Click close and use this close option to close the other window. The next verification process that we have to perform is known as layout versus schematic, or LVS. So this verification is done to make sure that the connection that we have across the layout of this inverter is exactly the same as the connection that we have created on our schematic. So again, to perform this verification, click on Asura and select Run LVS. And again, ensure some run name. Make sure that the same run name that you have given for DRC is used here, and make sure that the technology is selected and it's pointing to GPDK 180, and click OK once if this is the same. So now that we have got the results of LVS, which states that there is no mismatch between the layout and the schematic, just click S and again a window pops up stating that both our schematic and the layout matches. Now again, click on this file, click on this quit debug environment, and click on this command and click on close to close the VWL window. So now that we have done with the layout, the next task is to extract the RC information from this layout. As we know that any layer that we have drawn will have a capacitance with respect to the substrate, right? So now we have to measure those capacitance values. Also the metals and the polys that we have drawn will create some amount of resistance along its path. So we need to extract both those values by clicking on Asura and select Run RCX. So under this extraction tab, ensure that the extraction type is RNC and follow the same settings and click OK. Now once this process is done, the tool will automatically create one more view, which is known as AV extracted view. Now till now the inverter cell had the schematic view, the symbol view, and the layout view, and this new view which is known as AV extracted view. So we have totally created 4 such views. One can visualize the RNC component from the AV extracted view, for which you can just click on this Virtuoso Tools, Library Manager, and go to the go to your respective library and select the design cell, and you could be able to see that there is something known as AV extracted. So double click to open it, and here you could be able to see the same similar structure that we had for our layout. Use your Shift F key to visualize the things, and you could be able to zoom in and see that there are some resistances, and you can even find the capacitances along the length of the wires, and even the same is applicable across your transistors structures as well. Okay, so this is just for the visualization purpose. You can just close this AV extracted view. So the next task is to perform a post layout simulation. Now, to perform this post layout simulation, you need to create a new cell view which has been named as your test bench. So as shown here, my inverter test bench has the cell name as INV1X1_test. So using the same cell name, I'm going to create a new cell view which is known as config view. So for which, click on this file, click on new, and click on cell view, and make sure that you have given the same cell name of our inverter test bench. And now under this type, select the type as config and just click OK. And once you click OK, you end up having two windows. One is the new configuration window, the other one is the hierarchy window. Now out of this, make sure that you select the view as schematic, and in order to fill this global binding option, use the template option which is at the bottom, and ensure that you select the template name as Spectre. So Spectre is a simulator tool that we use normally for performing analog simulations. Just click OK, and that will fill this entire global binding options, and click OK to close this new configuration window as well. So once you're done with it, you could be able to see that the information that we had in our inverter test schematic is reflected onto this cell binding options as well. So right now the INV1X is the cell that we had in our schematic of our INV1X1 test bench. So I'll just open up the test bench schematic. So we had this VDC, the inverter design cell symbol, V-pulse, right? So all of these components are being listed over here. So now you could be able to see that this INV1X1 is right now pointing to schematic. Now we want the symbol which has been attached right now to schematic to get attached to AV extracted view rather than to the schematic. Now to perform this task, what you can do is just select the inverter design cell name, right click, and set the cell view which is right now pointing to schematic to AV extracted. So once this is done, right now the symbol that we have will actually point to our AV extracted view rather than to the schematic view. But to make it effective, we have to first save this option, and now you need to open this inverter test schematic window by clicking on this open button rather than opening it from the previous way. So click open and ensure that you have opened this test schematic under the config view rather than under the schematic view. So now from here we need to perform the normal simulation for our inverter design. But before that, ensure that this symbol is right now pointing to our AV extract view rather than the schematic. So how do we ensure that? Select this inverter symbol, right click, and click on Descend Read. So right now you could be able to see that the view that it is pointing is actually mapping to AV extracted view. So from here on you can perform this normal inverter simulation transient analysis. Now we can again switch back this symbol to point back to schematic from AV extracted by coming back to this hierarchy editor, right click on the cell that you want to invert it back and select the same set cell view but this time pointing to schematic. And now to make this effective, you have to click on save and then again click on this open. And now you can again go back to the symbol, right click and click on this descent read, and right now you could able to see that this symbol is right now is being attached to the schematic of our inverter. So click cancel and perform the simulation as before.